the man who harnessed infinity. About 200 years after Zeno pondered the nature of space, time, motion, and infinity, another thinker found infinity irresistible. His name was Archimedes. We've met him already in connection with the area of a circle, but he is legendary for many other reasons. For one thing, there are a lot of funny stories about him. Several portray him as the original math geek. For example, the historian Plutarch tells us that Archimedes could become so engrossed in geometry that it made him forget his food and neglect his person. That certainly rings true. For many of us mathematicians, meals and personal hygiene aren't top priorities. Plutarch goes on to say that when Archimedes was lost in his mathematics, he would have to be carried by absolute violence to bathe. It's interesting that he was such a reluctant bather, given that a bath is the setting for the one story about him that everybody knows. According to the Roman architect Vitruvius, Archimedes became so excited by a sudden insight he had in the bath that he leaped out of the tub and ran down the street naked, shouting, "Eureka! I have found it." Other stories cast him as a military magician, a warrior scientist, one-man death squad. According to these legends, when his home city of Syracuse was under siege by the Romans in 212 BCE, Archimedes, by then an old man, around 70, helped defend the city by using his knowledge of pulleys and levers to make fantastical weapons, war engines such as grappling hooks and giant cranes that could lift the Roman ships out of the sea and shake the sailors from them like sand being shaken out of a shoe. As Plutarch described the terrifying scene, a ship was frequently lifted up to a great height in the air, a dreadful thing to behold, and was rolled to and fro and kept swinging until the mariners were all thrown out, when at length it was dashed against the rocks or let fall. In a more serious vein, all students of science and engineering remember Archimedes for his principle of buoyancy. A body immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced, and his law of the lever, heavy objects placed on opposite sides of a lever will balance if and only if their weights are in inverse proportion to their distances from the fulcrum. Both of these ideas have countless practical applications. Archimedes' principle of buoyancy explains why some objects float and others do not. It also underlies all of naval architecture, the theory of ship stability, and the design of oil drilling platforms at sea. And you rely on his law of the lever, even if unknowingly, every time you use a nail clipper or a crowbar. Archimedes might have been a formidable maker of war machines, and he undoubtedly was a brilliant scientist and engineer. But what really puts him in the pantheon is what he did for mathematics. He paved the way for integral calculus. Its deepest ideas are plainly visible in his work, but then they aren't seen again for almost 2 millennia. To say he was ahead of his time would be putting it mildly. Has anyone ever been more ahead of his time? 2 strategies appear again and again in his work. The first was his ardent use of the infinity principle. To probe the mysteries of circles, spheres, and other curved shapes, he always approximated them with rectilinear shapes made of lots of straight, flat pieces, faceted like jewels. By imagining more and more pieces and making them smaller and smaller, he pushed his approximations ever closer to the truth, approaching exactitude in the limit of infinitely many pieces. This strategy demanded that he be a wizard with sums and puzzles, since he ended up having to add many numbers or pieces back together to arrive at his conclusions. His other distinguishing stratagem was blending mathematics with physics, the ideal with the real. Specifically, he mingled geometry, the study of shapes, with mechanics, the study of motion and force. Sometimes he used geometry to illuminate mechanics. Sometimes the flow went in the other direction, with mechanical arguments providing insight into pure form. It was by using both strategies with consummate skill that Archimedes was able to penetrate so deeply into the mystery of curves. Squeezing pi, when I walk to my office or go out with my dog for an evening stroll, the pedometer on my iPhone keeps track of how far I walk. The calculation is simple. The app estimates the length of my stride based on my height and counts how many steps I've taken. Then it multiplies those 2 numbers together. The distance traveled equals stride length times the number of steps taken. Archimedes used a similar idea to calculate the circumference of a circle and to estimate pi. Think of the circle as a track. It takes a lot of steps to walk all the way around. The path would look something like this. Each step is represented by a tiny straight line. By multiplying the number of steps by the length of each one, we can estimate the length of the track. It's only an estimate, of course, because the circle is not actually made up of straight lines. It's made up of curved arcs. When we replace each arc by a straight line, we're taking a slight shortcut. And so the approximation is sure to underestimate the true length of the circular track. But at least in theory, by taking enough steps and making them small enough, we can approximate the length of the track as accurately as we wish. Archimedes did a series of calculations like this, starting with a path made up of 6 straight steps. He began with a hexagon because it was a convenient base camp from which to embark on the more arduous calculations ahead. The advantage of the hexagon was that he could easily calculate its perimeter, the total length around the hexagon. It's 6 times the radius of the circle. Why 6? Because the hexagon contains 6 equilateral triangles, each side of which equals the circle's radius. 6 of the triangle's sides make up the perimeter of the hexagon. So the perimeter equals 6 times the radius. In symbols, P equals 6r. Then, since the circle's circumference C is longer than the hexagon's perimeter P, we must have C is greater than 6r. This argument gave Archimedes a lower bound on what we would call pi, written as the Greek letter pi, and defined as the ratio of the circumference to the diameter of the circle. Since the diameter d equals 2r, the inequality c is greater than 6r implies pi equals c over d, which equals c over 2r. Since c is greater than 6r, c over 2r is greater than 6r over 2r, which equals 3. Thus, the hexagon argument demonstrates pi is greater than 3. Of course, 6 is a ridiculously small number of steps, and the resulting hexagon is obviously a very crude caricature of a circle, but Archimedes was just getting started. Once he figured out what the hexagon was telling him, he shortened the steps and took twice as many of them. He did that by detouring to the midpoint of each arc, taking 2 baby steps instead of striding across the arc in one big step. Then he kept doing that, over and over again. A man obsessed, he went from 6 steps to 12, then 24, 48, and ultimately 96 steps, working out their ever-shrinking lengths to migraine-inducing precision. Unfortunately, it got progressively harder to calculate the step lengths as they shrank, because he had to keep invoking the Pythagorean theorem to find them. That required him to calculate square roots, a nasty chore to do by hand. Furthermore, to ensure that he was always underestimating the circumference, he had to make sure that his approximating fractions bounded the bothersome square midpoint 12 roots from below when he needed them to be underestimates and from above when he needed them to be overestimates. What I'm trying to say is that his calculation of pi was heroic, both logically and arithmetically. By using a 96 gon inside the circle and a 96 gon outside the circle, he ultimately proved that pi is greater than 3 plus 10/71 and less than 3 plus 10/70. Forget about math for a minute, just savor this result at a visual level. 3 plus 10/71 is less than pi is less than 3 plus 10/70. The unknown and forever unknowable value of pi is trapped in a numerical vice, squeezed between 2 numbers that look almost identical, except that the former has a denominator of 71 and the latter of 70. That latter result, 3 plus 10/70, reduces to 22/7, the famous approximation to pi that all students still learn today and that some unfortunately mistake for pi itself. The squeeze technique that Archimedes used, building on earlier work by the Greek mathematician Eudoxus, is now known as the method of exhaustion because of the way it traps the unknown number pi between 2 known numbers. The bounds tighten with each doubling, thus exhausting the wiggle room for pi. Circles are the simplest curves in geometry. Yet surprisingly, measuring them, quantifying their properties with numbers, transcends geometry. For example, you will find no mention of pi in Euclid's Elements, written a generation or 2 before Archimedes. You will find a proof by exhaustion that the ratio of a circle's area to the square of its radius is the same for all circles, but no hint that the universal ratio is close to 3.14. Euclid's omission was a signal that something deeper was needed. To come to grips with pi's numerical value required a new kind of mathematics, one that could cope with curved shapes. How to measure the length of a curved line or the area of a curved surface or the volume of a curved solid. These were the cutting-edge questions that consumed Archimedes and led him to take the first steps toward what we now call integral calculus. Pi was its first triumph. The tau of pi. It may seem strange to modern minds that pi doesn't appear in Archimedes' formula for the area of a circle, A equals RC over 2, and that he never wrote down an equation like C equals pi d to relate the circumference of a circle to its diameter. He avoided doing all that because pi was not a number to him. It was simply a ratio of two lengths, a proportion between a circle's circumference and its diameter. It was a magnitude, not a number. We no longer make this distinction between magnitude and number, but it was important in ancient Greek mathematics. It seems to have arisen from the tension between the discrete, as represented by whole numbers, and the continuous, as represented by shapes. The historical details are murky, but it appears that sometime between Pythagoras and Eudoxus, between the 6th and the 4th centuries BCE, somebody proved that the diagonal of a square was incommensurable with its side, meaning that the ratio of those two lengths could not be expressed as the ratio of two whole numbers. In modern language, someone discovered the existence of irrational numbers. The suspicion is that this discovery shocked and disappointed the Greeks, since it belied the Pythagorean credo. If whole numbers and their ratios couldn't even measure something as basic as the diagonal of a perfect square, then all was not number. This deflating letdown may explain why later Greek mathematicians always elevated geometry over arithmetic. Numbers couldn't be trusted anymore. They were inadequate as a foundation for mathematics. To describe continuous quantities and reason about them, the ancient Greek mathematicians realized they needed to invent something more powerful than whole numbers. So they developed a system based on shapes and their proportions. It relied on measures of geometrical objects, lengths of lines, areas of squares, volumes of cubes. All of these they called magnitudes. They thought of them as distinct from numbers and superior to them. This, I believe, is why Archimedes held pi at arm's length. He didn't know what to make of it. It was a strange, transcendent creature, more exotic than any number. Today we accept pi as a number, a real number, an infinite decimal, and a fascinating one at that. My children certainly were intrigued by it. They used to stare at a pie plate hanging in our kitchen that had the digits of pi running around the rim and spiraling in toward the center, shrinking in size as they swirled into the abyss. For them, the fascination had to do with the random-looking sequence of digits, never repeating, never showing any pattern at all, going on forever, infinity on a platter. The first few digits in pi's infinite decimal expansion are 3. 131592653589793 38462643 832795 028841971693 935 and 05820974 . We will never know all the digits of pi. Nevertheless, those digits are out there, waiting to be discovered. As of this writing, 22 trillion digits have been computed by the world's fastest computers. Yet 22 trillion is nothing compared to the infinitude of digits that define the actual pi. Think of how philosophically disturbing this is. I said that the digits of pi are out there, but where are they exactly? They don't exist in the material world. They exist in some Platonic realm, along with abstract concepts like truth and justice. There's something so paradoxical about pi. On the one hand, it represents order, as embodied by the shape of a circle, long held to be a symbol of perfection and eternity. On the other hand, pi is unruly, disheveled in appearance, its digits obeying no obvious rule, or at least none that we can perceive. Pi is elusive and mysterious, forever beyond reach. Its mix of order and disorder is what makes it so bewitching. Pi is fundamentally a child of calculus. It is defined as the unattainable limit of a never-ending process. But unlike a sequence of polygons steadfastly approaching a circle or a hapless walker stepping halfway to a wall, there is no end in sight for pi, no limit we can ever know. And yet pi exists. There it is, defined so crisply as the ratio of two lengths we can see right before us. The circumference of a circle and its diameter. That ratio defines pi, pinpoints it as clearly as can be, and yet the number itself slips through our fingers. With its yin and yang binaries, pi is like all of calculus in miniature. Pi is a portal between the round and the straight. A single number yet infinitely complex, a balance of order and chaos. Calculus, for its part, uses the infinite to study the finite, the unlimited to study the limited, and the straight to study the curved. The infinity principle is the key to unlocking the mystery of curves, and it arose here first in the mystery of pi. Cubism meets calculus. Archimedes went deeper into the mystery of curves, again guided by the infinity principle, in his treatise The Quadrature of the Parabola. A parabola describes the familiar arc of a three-point shot in basketball or water coming out of a drinking fountain. Actually, those arcs in the real world are only approximately parabolic. A true parabola, to Archimedes, would have meant a curve obtained by slicing through a cone with a plane. Imagine a meat cleaver slicing through a dunce cap or a conical paper cup. The cleaver can make different kinds of curves depending on how steeply it cuts through the cone. A slice parallel to the base of a cone makes a circle. A slightly steeper cut produces an ellipse. Circle ellipse. A cut that has the same slope as the cone itself produces a parabola. Viewed in the plane of the slice, the parabola appears as a graceful, symmetrical curve with a line of symmetry down its middle. This line is called the parabola's axis. In his treatise, Archimedes set himself the challenge of working out the quadrature of a parabolic segment. In more modern language, a segment of a parabola means the curved region lying between the parabola and a line that cuts across it obliquely. Finding its quadrature means expressing its unknown area in terms of the known area of a simpler shape, like a square, rectangle, triangle, or other rectilinear figure. The strategy used by Archimedes was astonishing. He reimagined the parabolic segment as infinitely many triangular shards glued together like pieces of broken pottery. Parabola, parabola axis, parabolic segment. The shards came in an endless hierarchy of sizes. One big triangle, two smaller ones, four smaller still, and so on. His plan was to find all their areas and then add them back together to calculate the curved area he was wondering about. It took a kaleidoscopic leap of artistic imagination to see a smooth, gently curving parabolic segment as a mosaic of jagged shapes. If he had been a painter, Archimedes would have been the first cubist. To carry out his strategy, Archimedes first had to find the areas of all the shards. But how, precisely, were those shards to be defined? After all, there are countless ways to piece triangles together to form a parabolic segment, just as there are countless ways to smash a plate into jagged bits. The biggest triangle could look like this, or this, or this. He came up with a brilliant idea, brilliant because it established a rule, a consistent pattern that held from one level of the hierarchy to the next. He imagined sliding the oblique line at the base of the segment upward while keeping it parallel to itself until it just barely touched the parabola at a single point near the top. That special point of grazing contact is called a point of tangency, from the Latin root tangere, meaning touching. It defined the third corner of the big triangle, the other two being the points where the oblique line cut the parabola. Archimedes used the same rule to define the triangles at every stage in the hierarchy. At the second stage, for example, the triangles looked like this. Notice that the sides of the big triangle now play the role of the oblique line used earlier. Next, Archimedes invoked known geometrical facts about parabolas and triangles to relate one level of the hierarchy to the next. He proved that each newly created triangle had 1/8 as much area as its parent triangle. Thus, if we say that the first, biggest triangle occupies 1 unit of area, that triangle will serve as our area standard. Then its two daughter triangles together occupy 1/8 plus 1/8 equals 1/4 as much area. At each subsequent stage, the same rule applies. The daughter triangles always contribute a total of 1/4 as much area as their parent does. So the total area of the parabolic segment, reassembled from the whole infinite hierarchy of shards, must be area equals 1 plus 4 plus 116 plus 1 4 plus 1, 1. An infinite series in which each term is 1/4 of the term preceding it. There's a shortcut to sum this kind of infinite series, which is known in the trade as a geometric series. The trick is to cancel all but one of its infinitely many terms by multiplying both sides of the equation for area by 4 and subtracting the original sum from it. Watch. Multiplying each term by 4 in the infinite series above gives. The magic happens between the next to last line and the last line above. The right-hand side of the last line equals 4 plus area, because the original sum, area equals 1 plus 1/4 plus 1/16 plus ... has, like a phoenix, been reborn in the terms following the 4 in the next to last line. So 4 times area equals 4 plus area. Subtract 1 area from both sides to get 3 times area equals 4. Thus, area equals 4/3. In other words, the parabolic segment has 4/3 the area of the big triangle. A cheesy argument, Archimedes would not have approved of the legerdemain above. He arrived at the same result by a different route. He resorted to a subtle style of argumentation often described as double reductio ad absurdum, a double proof by contradiction. He proved that the area of the parabolic segment could not be less than 4/3 or greater than 4/3, so it must equal 4/3. As Sherlock Holmes later put it, when you have 4 times area equals 4 times the quantity 1 plus 1/4 plus 1/16 plus 1/64 plus ... A equals 4 plus 4 over 4 plus 4 over 16 plus 4 over 64 plus ... equals 4 plus 1 plus 4 plus 1 plus ... equals 4 plus area. Eliminated the impossible, whatever remains, however improbable, must be the truth. What's conceptually crucial here is that Archimedes eliminated the impossible with arguments based on a finite number of shards. He showed that their combined area could be made as close to 4/3 as desired, closer than any prescribed tolerance, simply by taking enough of them. He never had to summon infinity. So everything about his proof was ironclad. It still meets the highest standards of rigor today. The gist of his argument becomes easy to understand if we put it in everyday terms. Suppose 3 people want to share 4 identical slices of cheese. The common-sense solution would be to give each person a slice, then cut the remaining slice into thirds and hand them out. That's fair. In total, everyone would get 1 plus 1/3 equals 4/3 of a slice. But suppose the 3 people happen to be mathematicians who are milling around the food table before the seminar, eyeing the last 4 slices of cheese. The cleverest of the 3, coincidentally named Archimedes, might suggest the following solution. I'll take a slice and you guys take yours, which leaves 1 more for us to share. Euclid, cut that leftover slice into quarters, not thirds, and everyone, take 1/4 of that leftover slice. We're going to keep doing this, always cutting what's left over into 4 equal portions until the remaining crumb is of no interest to anyone, okay? Eudoxus, stop whining. First leftover, second leftover. 4. How many slices of cheese, total, would each of them get to eat if this were to go on indefinitely? One way to look at it is to keep a running tally of how many slices each person gets. After round 1, each gets 1 slice. After round 2, when the quarter slices are passed out, each person has accumulated 1 plus 1/4 slices. After round 3, when the quarters are themselves quartered into 16ths, the running total for each is 1 plus 1/4 plus 1/16 slices, and so on. Loosely speaking, each of the 3 people would eventually get to eat 1 plus 1/4 plus 1/16 plus ... slices in total if the cutting went on forever. And since this amount must represent 1/3 of the original 4 slices, it must be that 1 plus 1/4 plus 1/16 plus ... equals 1/3 of 4, which is 4/3. In the quadrature of the parabola, Archimedes gave an argument very close to this, including a diagram with squares of different sizes, but he never invoked infinity or used the counterpart of the 3 dots above to signify that the sum went on endlessly. Rather, he phrased his argument in terms of finite sums so that it was unimpeachably rigorous. His key observation was that the tiny square in the upper right corner, the current leftover remaining to be shared, could be made smaller than any given amount by considering a sufficiently large but finite number of rounds. And by similar reasoning, the finite sum 1 plus 1/4 plus 1/16 plus ... plus 1/4 n, the total amount of cheese that each person gets, could be made as close to 4/3 as desired by making n large enough. So the only possible answer was 4/3. The method. It's at this point that I begin to feel real affection for Archimedes, because he does something in one of his essays that few geniuses ever do. He invites us in and reveals how he thinks. I'm using the present tense here because the essay is so intimate. It feels like he's speaking to us today. He shares his private intuition, a vulnerable, soft-bellied thing, and says he hopes that future mathematicians will use it to solve problems that eluded him. Today this secret is known as the method. I never heard of it in calculus class. We don't teach it anymore, but I found the story of it and the idea behind it enthralling and astounding. He writes about it in a letter to his friend Eratosthenes, the librarian at Alexandria, and the only mathematician of his era who could understand him. He confesses that even though his method does not furnish an actual demonstration of the results he's interested in, it helps him figure out what's true. It gives him intuition. As he says, it is easier to supply the proof when we have previously acquired, by the method, some knowledge of the questions than it is to find it without any previous knowledge. In other words, by noodling around, playing with the method, he gets a feel for the territory. And that guides him to a watertight proof. This is such an honest account of what it's like to do creative mathematics. Mathematicians don't come up with the proofs first. First comes intuition. Rigor comes later. This essential role of intuition and imagination is often left out of high school geometry courses, but it is essential to all creative mathematics. Archimedes concludes with the hope that there will be some among the present as well as future generations who, by means of the method here explained, will be enabled to find other theorems which have not yet fallen to our share. That almost brings a tear to my eye. This unsurpassed genius, feeling the finiteness of his life against the infinitude of mathematics, recognizes that there is so much left to be done, that there are other theorems which have not yet fallen to our share. We all feel that, all of us mathematicians. Our subject is endless. It humbled even Archimedes himself. The first mention of the method appears at the beginning of the essay on the quadrature of the parabola, before the cubist proof with the shards. Archimedes confesses that the method led him to that proof and to the number 4/3 in the first place. What is the method, and what is so personal, brilliant, and transgressive about it? The method is mechanical. Archimedes finds the area of the parabolic segment by weighing it in his mind. He thinks of the curved parabolic region as a material object. I'm picturing it as a thin sheet of metal, carefully trimmed into the desired parabolic shape. And then he places it at one end of an imaginary balance scale. Or, if you prefer, think of it as being seated at one end of an imaginary seesaw. Next, he figures out how to counterbalance it against a shape he already knows how to weigh, a triangle. From this, he deduces the area of the original parabolic segment. It's an even more imaginative approach than the cubist, geometric, or shards and triangles technique of his that we discussed earlier, because in this case, he's going to build the imaginary seesaw as part of the calculation and design it to comport with the parabola's dimensions. Together, they will produce the answer he seeks. He starts with the parabolic segment and tilts it to ensure that the parabola's symmetry axis is vertical. Then he builds the seesaw around it. The instruction manual reads as follows: draw the big triangle inside the parabolic segment, as before, and label it ABC. As in the cubist proof, this triangle is again going to serve as an area standard. The parabolic segment will be compared to it and will turn out to have 4/3 its area. Axis ABC next enclose the parabolic segment in a much bigger triangle ACD. The triangle's top side is chosen to be a line tangent to the parabola at the point C. Its base is the line AC, and its left side is a vertical line that extends upward from A until it meets the top side at point D. Using standard Euclidean geometry, Archimedes proves that this huge outer triangle ACD has 4 times the area of the inner triangle ABC. That fact will become important later. Set it aside for now. The next step is to build the rest of the seesaw, its lever, its two seats, and its fulcrum. The lever is the line that joins the two seats. That line starts at C, goes through B, emerges from the huge outer triangle at F, the fulcrum, and continues to the left until it hits a point S, the seat. The condition that defines S is that it's as far from F as C is. In other words, F is the midpoint of the line cédinish SC. Now comes the stunning insight that underlies the whole conception. Using known facts about parabolas and triangles, Archimedes proves that he can balance the huge outer triangle against the parabolic segment if he thinks about them one vertical line at a time. He regards them both as being composed of infinitely A, D, B, C, A, D, F, S, B, C, many parallel lines. Those lines are like infinitesimally thin slats or ribs. Here's a typical pair of them, defined by a single vertical line through both shapes. On that line, a short rib connects the base to the parabola, and a tall rib connects the base to the top side of the huge outer triangle. His amazing insight is that these ribs balance each other perfectly, like kids playing on a seesaw, as long as they sit in the right places. He proves that if he slides the short rib over to the point S and leaves the tall rib in place, they balance. FS, short rib. FS, tall rib, short rib, sits at S, tall rib, stays in place. FSC, the same is true for every vertical slice. No matter which vertical slice you take, the short rib always balances the tall rib if you slide the short rib to S and leave the tall rib in place. So the two shapes balance each other, rib by rib. All the ribs from the parabola end up at S. Together, they balance all the ribs from the huge outer triangle ACD. And since those ribs haven't moved, that means all the parabolic mass shifted to S balances the huge triangle right where it is. Next, Archimedes replaces the infinitely many ribs of the huge outer triangle with an equivalent point of their own, called the triangle's center of gravity. It serves as a proxy. As far as seesaws are concerned, the huge triangle acts as if its entire mass were concentrated at that single center of gravity. That location, Archimedes has already shown in other work, lies on the line FC at a point precisely 3 times closer to the fulcrum F than S is. So, since the entire mass of the triangle sits 3 times closer to the pivot point, the parabolic segment must weigh 1/3 as much as the huge triangle in order for them to balance. That's the law of the lever. Therefore, the area of the parabolic segment must be 1/3 that of the huge outer triangle ACD. And since that outer triangle has 4 times the area of the inner triangle ABC, the fact we set aside earlier, Archimedes deduces that the parabolic segment must have 4/3 the area of the triangle ABC inside it, ... just as we found earlier by summing the infinite series of triangular shards. I hope I've managed to convey what an acid trip of an argument this is. Instead of a potter reassembling shards, here Archimedes is more like a butcher. He takes the tissue of the parabolic region apart, one vertical strip at a time, and hangs all these infinitesimally thin strips of flesh from a hook at S. The total weight of all the flesh stays the same as it was back when it was an intact parabolic segment. It's just that he has shredded the original shape into lots of vertical, stringy strips, all hanging from the same meat hook. It's such a weird image. Maybe we should stick with seesaws. Why did I call this argument transgressive? Because it traffics with completed infinity. At one stage, Archimedes openly describes the outer triangle as being made up of all the parallel lines inside itself. That, of course, is taboo in Greek mathematics. There's a continuous infinity of these parallel lines, these vertical ribs. He's openly thinking of the triangle as a completed infinity of ribs. In doing so, he's unleashing the golem. Likewise, he describes the parabolic segment as being made up of all the parallel lines drawn inside the curve. Dallying with completed infinity lowers the status of this reasoning, in his estimation, to a heuristic, a means of finding an answer, not a proof of its correctness. In his letter to Eratosthenes, he downplays the method as giving nothing more than a sort of indication that the conclusion is true. Whatever its logical status, Archimedes' method has an e pluribus unum quality to it. This Latin phrase, the motto of the United States, means out of many, one. Out of the infinitely many straight lines making up the parabola, one area emerges. Thinking of that area as a mass, Archimedes shifts it, line by line, to the far left seat on the seesaw. The infinitude of lines is thereby represented by a single mass seated at a single point. The one replaces the many and stands for it, representing it perfectly and faithfully. The same is true for the counterbalancing outer triangle on the right of the seesaw. Out of its continuum of vertical lines, one point is chosen, its center of gravity. It too stands for the whole. Infinity collapses to unity, e pluribus unum. Except this is not poetry or politics. This is the beginning of integral calculus. Triangles and parabolic regions are apparently and mysteriously equivalent, in some sense that Archimedes could not quite make rigorous, to infinitudes of vertical lines. Although Archimedes seems embarrassed by his dalliance with infinity, he is brave enough to own up to it. Anyone trying to measure a curved shape, to find the length of its boundary or the area or the volume inside it, has to grapple with the limit of an infinite sum of infinitesimally small pieces. Careful souls may try to sidestep that necessity, finessing it with the method of exhaustion. But at bottom, there is no escaping it. Coping with curved shapes means coping with infinity, one way or another. Archimedes is open about this. When he needs to, he can dress up his proofs in respectable garb, sporting finite sums and the method of exhaustion. But in private, he's dirty. He admits to weighing shapes in his mind, dreaming of levers and centers of gravity, balancing regions and solids line by line, one infinitesimal piece at a time. Archimedes went on to apply the method to many other problems about curved shapes. For example, he used it to discover the center of gravity of a solid hemisphere, a paraboloid, and segments of ellipsoids and hyperboloids. His favorite result, which he loved so much that he asked that it be carved on his tombstone, concerned the surface area and volume of a sphere. Picture a sphere sitting snugly in a cylindrical hatbox. Using the method, Archimedes discovered that the sphere has 2/3 the volume of the enclosing hatbox, as well as 2/3 of its surface area, assuming the top and bottom lids are also counted in the hatbox's surface area. Notice that he didn't give formulas for the volume or the surface area of the sphere, as we would today. Rather, he phrased his results as proportions. That's classic Greek style. Everything was expressed as a proportion. An area was compared to another area, a volume to another volume. And when their ratio involved small whole numbers, as they do here with 3 and 2, and as they did with 4 and 3 in the quadrature of the parabola, that must have been a source of particular pleasure to him. After all, those same ratios, 3.2 and 4:3, held special significance to the ancient Greeks because of their central role in the Pythagorean theory of musical harmony. Recall that when two otherwise identical strings with lengths in the ratio 3.2 are struck, they harmonize beautifully, separated in pitch by an interval known as a fifth. Similarly, strings in a 4:3 ratio produce a fourth. These numerical coincidences between harmony and geometry must have delighted Archimedes. His words in his essay On the Sphere and Cylinder suggest just how tickled he was. Now these properties were all along naturally inherent in the figures, but remained unknown to those who were before my time engaged in the study of geometry. Ignore how proud he sounds and focus instead on his claim that the properties he discovered were all along naturally inherent in the figures, but remained unknown. Here he is expressing a particular philosophy of mathematics dear to the hearts of all working mathematicians. We feel we are discovering mathematics. The results are there, waiting for us. They have been inherent in the figures all along. We are not inventing them. Unlike Bob Dylan or Toni Morrison, we are not creating music or novels that never existed before. We are discovering facts that already exist, that are inherent in the objects we study. Although we have creative freedom to invent the objects themselves, to create idealizations like perfect spheres and circles and cylinders, once we do, they take on lives of their own. When I read the way Archimedes expresses his pleasure at unveiling the surface area and volume of the sphere, I feel like I'm feeling the same things he felt. Or rather, that he was feeling the same things I feel and that all of my colleagues feel when we do mathematics. Although we are told that the past is a foreign country, it may not be foreign in every respect. People we read about in Homer and the Bible seem a lot like us. And the same appears to be true of ancient mathematicians, or at least of Archimedes, the only one who let us into his heart. 22 centuries ago, Archimedes wrote a letter to his friend Eratosthenes, the librarian at Alexandria, essentially sending him a mathematical message in a bottle that virtually no one could appreciate, but that he hoped might somehow sail safely across the seas of time. He had shared his private intuition, his method, in the wish that it might enable future generations of mathematicians to find other theorems which have not yet fallen to our share. The odds were against him. As always, the ravages of time were cruel, kingdoms fell and libraries were burned. Manuscripts decayed, not a single copy of the method was known to have survived the Middle Ages. Although Leonardo da Vinci, Galileo, Newton, Ingenuity, and other geniuses of the Renaissance and the scientific revolution pored over what was left of Archimedes' treatises, they never had a chance to read the method. It was thought to be irretrievably lost. And then, miraculously, it was found. In October 1998, a battered medieval prayer book came up for auction at Christie's and sold to an anonymous private collector for $2.2 million. Barely visible under its Latin prayers lay faint geometrical diagrams and mathematical text written in 10th century Greek. The book is a palimpsest. In the 13th century, its parchment folios had been washed and scraped clean of the original Greek and overwritten with Latin liturgical text. Fortunately, the Greek was not completely obliterated. It contains the only surviving copy of Archimedes' method. The Archimedes palimpsest, as it is now known, first came to light in 1899 in a Greek Orthodox library in Constantinople. It spent the Renaissance and the scientific revolution undetected in a prayer book in the monastery of St. Sabas near Bethlehem. It now lives in the Walters Art Museum in Baltimore, where it has been lovingly restored and examined using the latest imaging technology. Archimedes. Today, from computer animation to facial surgery, Archimedes' legacy lives on today. Consider the computer-animated movies that our kids love to watch. The characters in films like Shrek, Finding Nemo, and Toy Story seem lifelike and real, in part because they embody an Archimedean insight. Any smooth surface can be convincingly approximated by triangles. For example, here are 3 triangulations of a mannequin's head. The more triangles we use and the smaller we make them, the better the approximation becomes. What's true for mannequins is equally true for ogres, clownfish, and toy cowboys. Just as Archimedes used a mosaic of infinitely many triangular shards to represent a segment of a smoothly curved parabola, modern-day animators at DreamWorks created Shrek's round belly and his cute little trumpet-like ears out of tens of thousands of polygons. Even more were required for a tournament scene in which Shrek battled local thugs. Each frame of that scene took over 45 million polygons. But there was no trace of them anywhere in the finished movie. As the infinity principle teaches us, the straight and the jagged can impersonate the curved and the smooth. When Avatar was released nearly a decade later, in 2009, the level of polygonal detail became more extravagant. At director James Cameron's insistence, animators used about 1 million polygons to render each plant on the imaginary world of Pandora. Given that the movie took place in a lush virtual jungle, that amounted to a lot of plants, and a lot of polygons. No wonder Avatar cost $300 million to produce. It was the first movie to use polygons by the billions. The earliest computer-generated movies used far fewer polygons. Nonetheless, the computation seemed staggering at the time. Consider Toy Story, released in 1995. Back then, it took a single animator a week to sync an 8-second shot. The whole film took 4 years and 800,000 hours of computer time to complete. As Pixar co-founder Steve Jobs told Wired, there are more PhDs working on this film than any other in movie history. Soon after Toy Story came Jerry's Game, the first computer-animated film with a human main character. This funny, sad story of a lonesome old man who plays chess with himself in the park won the 1998 Academy Award for Best Animated Short Film. Like other characters generated by a computer, Jerry was built from angular shapes. At the beginning of this section, I showed a computer graphic of a face made from ever more triangles. In much the same way, the animators at Pixar fashioned Jerry's head from a complex polyhedron, a three-dimensional gem-like shape that consisted of about 4,500 corners with flat facets in between them. The animators subdivided those facets repeatedly to create an increasingly detailed depiction. This subdivision process took up much less memory in the computer than earlier methods had, and it allowed for much faster animations. It was a revolutionary advance in computer animation at the time. But in spirit, it channeled Archimedes. Recall that to estimate pi, Archimedes started with a hexagon, then subdivided each of its sides and pushed their midpoints out to the circle to generate a 12-gon. After another subdivision, the 12-gon became a 24-gon, then a 48-gon, and finally a 96-gon, each encroaching ever more closely on its target, a limiting circle. Likewise, Jerry's animators approximated the character's wrinkly forehead, his protuberant nose, and the folds of skin in his neck by repeatedly subdividing a polyhedron. By repeating that process enough times, they could make Jerry look like what he was intended to be, a puppet-like character who conveyed a wide range of human feeling. A few years later, a Pixar rival, DreamWorks, took the next steps forward in realism and emotional expressiveness in their story of a smelly, grouchy, heroic ogre named Shrek. Although he never existed outside a computer, Shrek seemed practically human. That was partly because the animators took such great care to reproduce human anatomy. Underneath his virtual skin, they built virtual muscle, fat, bones, and joints. It was done so faithfully that when Shrek opened his mouth to speak, the skin on his neck formed a double chin. Which brings us to another field where Archimedes' idea of polygonal approximation has proved useful: facial surgery for patients with severe overbites, misaligned jaws, or other congenital malformations. In 2006, the German applied mathematicians Peter Döflard, Martin Weiser, and Stefan Zachow reported the results of their work using calculus and computer modeling to predict the outcomes of complex facial surgeries. The team's first step was to build an accurate map of a patient's facial bone structure. To do so, they scanned the patients with computerized tomography, CT, or magnetic resonance imaging, MRI. The results gave information about the three-dimensional configuration of facial bones in the skull, from which the researchers created a computer model of the patient's face. The model was not just geometrically accurate, it was biomechanically accurate. It incorporated realistic estimates of the material properties of skin and soft tissues such as fat, muscle, tendons, ligaments, and blood vessels. With the help of the computer model, surgeons could then perform operations on virtual patients, similar to how fighter pilots sharpen their skills in flight simulators. Virtual bones in the face, jaw, and skull could be cut, relocated, augmented, or removed entirely. The computer calculated how the virtual soft tissue behind the face would move and reconfigure itself in response to stresses produced by the face's new bone structure. The results of such simulations were helpful in several ways. They alerted the surgeons to possible adverse effects the procedures could have on vulnerable structures like nerves, blood vessels, and the roots of teeth. They also revealed what the patient's face would look like post-operatively, since the model predicted how the soft tissues would reposition themselves after the patient healed. Another advantage was that the surgeons could prepare better for the actual operations in light of the simulated results, and the patients could make better decisions about whether to have the operations. Archimedes came in when the researchers modeled the smooth, two-dimensional surface of the skull with an enormous number of triangles. The soft tissue posed its own geometrical challenges. Unlike the skull, soft tissue forms a fully three-dimensional volume. It fills the complicated space in front of the skull and behind the skin of the face. The team represented it by hundreds of thousands of tetrahedrons, the three-dimensional counterparts of triangles. In the image below, the skull surface is approximated by 250,000 triangles. They're too small to be seen, and the volume of soft tissue consists of 650,000 tetrahedrons. The array of tetrahedrons allowed the researchers to predict how the patient's soft tissues would deform after surgery. Roughly speaking, soft tissue is a deformable yet springy material, a bit like rubber or spandex. If you pinch your cheek, it changes shape. When you let go, it returns to normal. Ever since the 1800s, mathematicians and engineers have used calculus to model how different materials stretch, bend and twist when they are pushed, pulled, or sheared in various ways. The theory is most highly developed in the more traditional parts of engineering, where it's used to analyze the stresses and strains in bridges, buildings, airplane wings, and many other structures made of steel, concrete, aluminum, and other hard materials. The German researchers adapted the traditional approach to soft tissues and found that it worked well enough to be valuable to surgeons and patients alike. Their basic idea was this: think of the soft tissue as a meshwork of tetrahedrons connected to one another like beads connected by elastic threads. The beads represent tiny portions of tissue. They are tied together elastically because, in reality, atoms and molecules in the tissue are linked by chemical bonds. Those bonds resist stretching and compression, which is what endows them with elasticity. During a virtual operation, a surgeon cuts bones in the virtual face and relocates some of the bone segments. When a piece of bone is moved to a new place, it pulls on the tissues it's connected to, which in turn pull on their neighboring tissues. The meshwork reconfigures itself due to the effect of cascading forces. As pieces of tissue move, they change the forces they exert on their neighbors by stretching or compressing the bonds between them. Those affected neighbors themselves readjust, and so on. Keeping track of all the resulting forces and displacements is a massive calculation that can be done only by computer. Step by step, an algorithm updates the myriad of forces and moves the tiny tetrahedrons accordingly. Ultimately, all the forces balance and the tissue settles into its new equilibrium state. That's the new shape of the patient's face that the model predicts. In 2006, Duflar, Weiser, and Zachow tested their model's predictions against the clinical outcomes of about 30 surgical cases. They found that the model worked remarkably well. As one measure of its success, it correctly forecast, to within 1 millimeter, the position of 70% of the patient's facial skin. Only 5 to 10% of the skin surface deviated by more than 3 millimeters from its predicted post-operative location. In other words, the model could be trusted. And it was certainly better than guesswork. Here's an example of one patient before and after surgery. The 4 panels show his profile before the operation. Far left. The computer model of his face at that time, mid-left. The predicted outcome of the surgery, mid-right. And the actual outcome, far right. Look at the position of his jaw before and after. The results speak for themselves. Onward to the mystery of motion. I am writing these words the day after a blizzard. Yesterday was March 14th, Pi Day, and we got over a foot of snow. This morning, while I was shoveling my driveway for the 4th time, I watched jealously as a small tractor with a front-mounted snow thrower made its way easily down the sidewalk across the street. It used a rotating screw blade to pull snow into the machine and then ejected it onto my neighbor's yard. This use of a rotating screw for propelling something goes back to Archimedes, at least according to legend. In his honor, today we call it an Archimedean screw. He is said to have come up with the invention during a trip to Egypt, although it may have been used much earlier by the Assyrians. It was developed to lift water from a low-lying area up to an irrigation ditch. Today, cardiac assist devices use Archimedean screw pumps to support circulation when the heart's left ventricle is impaired. But apparently, Archimedes did not want to be remembered for his screws, or his war engines, or any other practical inventions. He never left us any writings about them. He was proudest of his inventions in mathematics. Which also gets me thinking that it is fitting to be reflecting on his legacy on Pi Day. In the 2200 years since Archimedes trapped pi, numerical approximations to pi have been improved many times, but always by using mathematical techniques that Archimedes himself introduced. Approximations by polygons or by infinite series. More broadly, his legacy was the first principled use of infinite processes to quantify the geometry of curved shapes. At this he was unrivaled, and he remains so to this day. Yet the geometry of curved shapes takes us only so far. We also need to know how things move in this world, how human tissue shifts after surgery, how blood flows through an artery, how a ball flies through the air. On this, Archimedes was silent. He gave us the science of statics, of bodies balancing on levers and floating stably in water. He was a master of equilibrium. The territory ahead concerned the mysteries of motion.